In this video, we are going to discuss the continuity of functions that go from some metric space X into Rk. Okay, these functions are going to take a point X in the metric space, and they are going to return a vector in Rk where each component is a function of the original point. Okay, so we are going to have k coordinate functions here. Okay, and remember we are assuming X is a metric space. Okay, so what does it mean to be continuous for a function like this? So f of x defined just as before. Okay, here we have is continuous if and only if each of the individual functions f by x is continuous. All right, so the proof of this theorem is actually quite straightforward. To prove this theorem, we only need to realize that f of x minus f of y for the full function, this is just the square root of the sum from 1 to k of fi x minus fi y square. Okay, so somehow if all fi are continuous, that means that there for every epsilon bigger than 0, that there exists some delta I for each fi, such that if x minus y less than delta I, then f of xi minus fi y is less than epsilon. Okay. Now notice here, we can just take delta. Well, actually, let's write it here carefully. We can take delta, the minimum of all the delta I. Okay. And then we can, this definition of continuity that we wrote, we will be able to do the same, just writing delta every time instead of the delta I. Okay. This is a way to make all of them the same. And now once we have this, what do we get? We get that fx minus fy equals the square root of k times epsilon square. Actually, not equal, less, because then see what was inside of the square root. It was all these quantities that we know they are less than epsilon. So we get epsilon squared k times, right? And then if we don't like the way this looks, this already gives continuity, okay? Because here we have something that is very small. So what we're saying is for every epsilon, there exists some delta such that if x minus y is less than delta, then fx minus fy is very close, okay? But let's say we want to call this epsilon, okay? I'm trying to use like a different epsilon. So you will see this in books very often, that they use very strange values of epsilon out of nowhere. This is how it works. What I'm going to do here is to say little epsilon squared equals capital epsilon squared divided by k. Okay, so that means epsilon equals capital epsilon divided by square root of k. Okay, so what I'm going to do is I'm going to go back here where I said for every epsilon. So I'm going to take a particular value of epsilon, which is this one, capital epsilon divided by square root of k. And if I do that, okay, see what happens. Here, okay, here what I'm going to get is k times the square root of k times epsilon squared divided by k. Okay, so here I'm going to get capital epsilon. So all I'm saying here is for every epsilon bigger than 0, there exists delta, which is the minimum of the delta I, okay, but we don't have to say that, such that x minus y less than delta implies fx minus fy less than epsilon, okay? And here what I'm going to, well, I just used the proof above, okay? So here, what did we prove? We have proved fi continuous implies vector f continuous. Okay, but we saw this was an if and only if, so we need to prove that if vector f is continuous, then all fi are continuous. But this is actually very similar, follows from the same identity. Okay, that's the definition of the magnitude of a vector, right? But here notice that because this is a sum of positive things, if I sum a bunch of, well, let's do it just with numbers, a1 plus a2 plus ak, if all of them are non-negative, then the sum is larger than any particular instance. Like you pick a2, so it will be bigger or equal than a2. All the other aj's are only making the sum bigger, okay? So this is bigger or equal than fjx minus fjy, okay? And here the square root and the square cancel out once I get rid of all the extra k minus 1 terms. Okay, but here, notice what we are saying is vector f continuous. That means for every epsilon bigger than 0, there exists delta bigger than 0 such that x minus y less than delta implies, let's create some space, implies vector fx minus vector fy less than epsilon. But this, with this, we are basically done, right? Because here, fjx minus fjy less or equal than vector fx minus vector fy, and this we just said is less than epsilon. So let's highlight here, for every epsilon there exists delta such that if x minus y is less than delta, then fjx minus fjy is less than epsilon. And that is the definition of continuity of fj. And we are done. Okay. Now, one more thing that follows from here on the fact, so we already know that the sum of functions, of continuous functions, is continuous, the product, the quotient, okay? So for example, well, this is a consequence, so let's call it corollary. Whenever we have vector functions f, j that are continuous from x to rk, okay, the sum is continuous and the dot product is continuous, okay? This follows from the properties for the component functions. Let's see some explicit examples. For instance, some very important functions that we are going to be using are the coordinate functions. So phi x, that is just the xi coordinate for every x in Rk. Okay, here we are using our metric space will be Rk. So these functions that give you the coordinates of a point x in Rk are continuous. On Rk. Okay. How is that? So for every epsilon bigger than 0, there exists delta bigger than 0 such that if x minus y less than delta, then phi x minus phi y less than epsilon. Okay, but now if we write what is what? So here we have xi minus yi. Okay. Here notice something very nice. Xi minus yi. Okay, this is less or equal than the square root of the sum from 1 to k of the xj minus yj square, okay, which is x minus y. Okay, so for example, we can take this, we want less than delta, but since the number that we are given is epsilon, what we can do is write epsilon, okay, and just take delta equal to epsilon. That will do for the definition, okay? So if we take delta equal to epsilon, then it's clear that for every epsilon, if x minus y here is less than epsilon, then phi I minus of x minus phi I of y is less than epsilon 2. Okay, this may sound a little silly because actually it's very easy. It's just not so easy to write carefully. Okay, but this function is clearly continuous. If this is not continuous, then we are done, right? Okay, these are called sometimes the coordinate functions of a point. But now the nice thing, once we know that these are continuous, then we can, since we know that the product of continuous functions is continuous, we can just multiply them together, right? We can multiply all of them if we wish, but we can also multiply them several times, each of them, and get powers, okay? Here would be, we would have n1 and so on. This would be non-negative integers. Okay, but this is continuous too. It's a product of continuous functions. But we don't have to stop there, because now we can also multiply by constants, okay, which is continuous too. So we can write, let's say, well, let's keep it like this, c times the whole thing that we wrote before. Okay, and that is continuous too. But we can even add these together. Okay. Now I will need different coefficients. So what I'm going to do is to index these coefficients by the exponents. Okay, so this is a sum that runs in the n1, nk. And these are polynomials. Polynomials in k variables. For example, I could be thinking of x1, x2, x3 plus 2x1 squared, x3 plus 3x1, x2 to the power 3, and so on. Okay, anything I want. I could even have negatives. Okay, so here the important thing, as long as it's a finite sum, okay, that means that there is a finite number of terms, then it's a polynomial, then it's a continuous function. Okay, because it's a sum of continuous functions. The coefficients I didn't mention, but these coefficients don't have to be necessarily real. They can be complex numbers, no problem. Okay, and we will still get the continuous function. And from here, we can go to rational functions. These are also continuous. Here, we could even take one of these polynomials. Okay, these are the rational functions. Take one polynomial divided by another polynomial, and that's a rational function. Here, different coefficients, of course, or same, but okay, and here we have different exponents. So this would be a rational function q of x, for example. And this one is continuous too. And one more function that I want to mention that is continuous is the absolute value, the modulus. Okay, the mapping x to the modulus of x. This one is continuous in Rk. And here, this we are going to see from the inequality x minus y, both in absolute value, less or equal than x minus y. This we saw a few weeks ago. okay? But this one gives the continuity, because as long as the x minus y is less than epsilon, so here again we would be taking delta equal epsilon, okay? For every epsilon bigger than 0, x minus y less than epsilon. If the x minus 1 less than epsilon, then x minus y, both in absolute value, less than epsilon 2. Okay, so the function is continuous. And finally, the composition of continuous functions. Okay. This allows us to take the modulus of a function vector f of x. Okay, and that is also going to be continuous, because it's the composition of the mapping in point 5, the modulus, and a continuous vector function f.